I'd like to introduce our speakers for tonight. Australia is a world leader in the use of remote operations to safely assess harsh or complex locations and overcome the tyranny of distance. The Australian Remote Operations for Space and Earth, which is called AROSE, consortium is leveraging this expertise and extending it further into space. This talk will have the CEO, Leanne Cunnold, and as well as Ben Harting and Stuart Buchan, both of them from Curtin University. I won't read out their bios, but would you please put your hands together to welcome them to the podium.
Thank you. Good evening, everyone. And who would have thought we'd be standing here talking about space? Well, I certainly wouldn't have thought that in my time. I've recently returned to Perth, recently, 2 years ago, but never did I think that I would be Perth in a career in space. So who's AROSE? Okay. So first of all, I'd like to tell you about the way AROSE was formed, the inspiring story. And actually, it's quite ironic because it was formed by two non-Australians who saw the potential that Australia has in remote asset monitoring. The first was Pamela Malroy, and she's a former astronaut. She's done about 38 days in space, and she's just had her Senate hearing to be the second in charge of NASA. So we're expecting any week now that she will be awarded that position. The second person was Russell Potopinski, and he was the head of robotics from Woodside. So I'm not too sure if people know Russell, but anyway, they were the two co-founders. And the story goes that they were having a very long lunch at Indiana Tea Rooms, and every time I tell this story, Russell says, Leanne, you must tell them that it was over Leanne Estate Art Series Chardonnay, the most important part of the story. So, okay, Russ. So basically over this long lunch, they had this big idea, and the idea was space tech transfer driven through remote operations. So Pam and Russ, and if any of you have ever met them or come across them, they're two hugely passionate people, and their passion gained momentum, and along the way they drew in our founding members, which were Woodside, Nova, and then Fugro, Fugro's Deep Sea, Curtin University, who are here today, University of Western Australia, and then we were also supported by the Western Australian Government. Then along the way, we've gained a few more partners, Fleet Technologies in South Australia, New South Wales University, QUT, who's actually worked on Perseverance, and then MDA. So MDA is a Canadian company. They have about 50 years heritage in space, and they were also inspired by the vision and came and joined AROSE. And in the next few weeks, we'll be adding to our consortium. I can't tell you the people's names, but another one is a space company, and another company is reeling around data management, high power compute company. So we're continuing to grow the consortium of members. So a lot of logos, but when you look at a technology stack, what does it mean? It means that we have capabilities in communications, in satellites, which you're going to hear more about today, in robotics, system integration, and then, as I mentioned, some more space capabilities and some data capabilities. So AROSE is actually an industry-led, non-for-profit consortium. And what we do is that we're solving the business challenges through the lens of remote operations. So that's really the scope that we have. And, to put it another way, we're really like the honest broker. So we take a customer problem, and then we look at our consortium of solution providers, and then we match them together so that they can collectively collaborate to solve the business issue at hand. But again, it's always through that lens of remote operations. So when you look at what our vision is, the vision is for Australia to be the trusted leader in remote operations science, technology and services in space and on Earth. And the way that we do this is through projects. So it's looking at the tech transfer from Earth to space and then space back to Earth again. And by standing up projects, the benefit of that is also that we're going to build our national capabilities, which then will help the future workforce, because it will help improve and develop the skills now and also for the next generation. And the other thing that we're trying to do is working alongside, in line with the Australian Space Agency, in line with their strategy and their key priorities, is working together to play a pivotal role in cementing Australia's place in the International Space Station. In actual fact, talking about space, one of the projects that we're working on now is a Break the Ice challenge, and it's with an American consortium, and they basically called us up to say, we need help on this project, and can you please, come to the table, because you have the capabilities of the exploration side. So what it is, it's taking, it's moving icy regolith, and from that extracting water, and then from that water will be used for sustained missions on Mars. So, we're talking about the moon, the lunar surface, sorry. We're talking about, 10 or more years away, but that's essentially what the project is. And so our contribution to that is the moving of the icy regolith. Now, when you think about it, 5-10 years ago, that was just, unconceivable. So it's really incredible how far we've actually come. So why is space important? And it's really important because when you innovate for space, you're really innovating for the harshest of all of the environments. You're learning how to ruggedize. It helps you learn how to make things smaller and lighter, because to transport a kilo to space is, a significant sum of money. So you absolutely need to make it smaller and lighter. And then the benefit of that is then the spin-offs from what we have from space, the spin-offs back down to Earth, so that we can optimise it across various sectors here. So, if we don't play in the space sector, then we will be disrupted by the future disruptors. And if I just talk about in general, some of the spin-offs that we all have benefited from space research, across the world, this is not just necessarily Australia, is, that your camera in your smartphone, CAT scans. Who has a pair of Nike shoes, running shoes? Running shoes, yeah, great. Okay, well that came from spacesuit technology. So, there's baby food formula. How do you get nutrients in that? Well, that's from dry food that, the astronauts had. Wireless headsets from space technology, so that the astronauts could be free to move around on their missions. So that's just an example of how space impacts, the research and the innovation into space has impacted our everyday life. So with that, I'm now going to hand over to the Curtin team, who's going to talk about a really exciting project for Australia, but also for Western Australia. And please welcome Ben. Thank you.
Thank you very much for having us here today. It's really great to be invited. I'm actually standing in for my boss, the Director of the Space Science and Technology Centre at Curtin, Phil Bland, also known as the John Curtin Distinguished Professor Phil Bland, and he's got a very long career in space. I'm only getting started, but I'll share a bit about our project, which I'm the project manager of. It's a bit of an interesting story how we got to doing space stuff. So we're actually a blue sky research group, Space Science and Technology Centre at Curtin. And the thing about our project and also my career, I got started looking for fireballs in the sky over Perth, over South Australia and across Australia, and eventually across the world. And that project's called the Desert Fireball Network. You can see it on the left out of the three circles there. one of the stations, and those are little stations that sit out in the desert with a full sky lens, capturing images of the sky all night, and finding the streaks in the sky, and then triangulating those streaks down to the ground. And I actually came out of my undergraduate degree and got caught up in that project, and I haven't seemed to be able to escape yet. And from there, I quickly went across to an interesting project rolling that out as a satellite tracking network. So we sort of took that technology that was made for blue sky research into fireballs and gave it a commercial application with our partner Lockheed Martin Aerospace Australia to develop it for tracking satellites. And we have incredible detection rate, something like 10,000 hits a night for satellites passing the sky over Australia. So that's been a really exciting journey. And part of that journey took us to the point where we thought, okay, we're building remote systems. We deal with really poor data connections out in the middle of the Nullarbor, out in the middle of the Woomera area. We've got solar power, we've got to deal with remote operations and limited connections, and a lot of these things are similar to the challenges you face building a satellite. And if any of you know about CubeSats, you know that there's this initiative that was started in the US basically to help education and research develop spacecraft skills and opportunities, and that's to carry small 10 centimetre by 10 centimetre, 10 by centimetre units. And we thought, okay, we're a university, we've got lots of students that are really keen to do space stuff, let's do that. And so we named our project Binar, which is the Noongar word for falling star or meteor, and sort of tied that back to our heritage in the Desert Fireball Network and our place here in Perth, that we were really proud of being part of Western Australia. So that's a little bit about us, and I guess a big part of this discussion is what are the barriers to space. So McKinsey & Co have done a lot of papers, but one in particular was an Aerospace and Defence report from last year that basically was looking at what are the barriers. And everyone seems to get stuck on the launch costs, and we hear a lot about the talk about launch costs, but we don't consider that even as launch costs come down, the cost of building and manufacturing spacecraft stays really high. And that's partly, as most of you, I assume, being in the industry, you would understand that that's a bespoke solution for every single spacecraft, and that's not a really effective way to do business. So one of the areas we've looked at is reducing the cost of manufacturing spacecraft and leveraging commodity manufacturing techniques in all of our work. This is, I wonder if this will play. So there's a bit of information you can, if you want to sort of follow along with us as we go on our journey, you can go to our website, which is binarspace.com, and just we'll be presenting a lot of the information as we go, just so that we can help people join in on our journey. And that journey is to take a 1U CubeSat, which is sort of pictured there, and use that really tiny form factor to get as much value into space as we can. That starts with research and education, and then it grows from there to look at what applications can we use a very small spacecraft with limited capabilities for, and then how can that leverage progression into manufacturing larger spacecraft. So taking the hard lessons in a small form factor and making sure we open a path forward to larger things. So typically, sorry about that. So typically in CubeSats, being an education thing, they tend to purchase lots of PCBs from different companies and sandwich them together in a bit of a tangle. And what you end up is each subsystem sits on its own board, and that subsystem's been tested independently and takes up its space. But as we've discussed, we're working with a very small volume. We've got 10 centimetres by 10 centimetres by 10 centimetres, and filling that whole thing with all these different boards that do simple things like manage power, determine your attitude, control your attitude, comm system, computer system, each GPS, power supply. Each of those holding one space on it actually makes for quite a large stack. And all we've done is condense that down onto a single board. So we've basically taken all those different methods and used the most modern techniques we can to integrate into a single PCB. At heart, we're an electronics group, so we've really focused on that. And a lot of that sort of condensation means that what we end up with is a platform that we can carry a lot more payload, so like the actual reason you put a spacecraft into space. So we typically talk about two sort of parts of a spacecraft. We talk about the bus, which is all of those things that you have to have. It's not really, they're not optional. They're the thing that keep the thing running. And then you have the payload, and that's really the purpose. And when you've got more bus than payload, it feels like the purpose of the mission is the bus, when in reality it should be the other way around. It should be minimizing that bus, making sure that the functionality is there, and focusing on the payload, the mission, the goal of the spacecraft. And so that's sort of the mentality that we've come into this with. So our project started at the end of 2017. 2018 was mainly sort of scoping out things with a group of students and building subsystems on boards, testing them in vacuum chambers, thermal environments and things like that, and sort of just determining, what's required to build a spacecraft and what's involved. And during that time, we actually approached most of the international providers of CubeSat subsystems, which is that stacked system that people typically go down, and we realised very quickly that one, they don't work on the time scale that universities need to. We have students passing through. We want to get them as much opportunity and skill building as we can in a short period of time, and to sort of break down those barriers for entry to space by having a skilled workforce coming out of university. And so waiting 3 months for a part to arrive from order is not really an acceptable timeline. So we went back to basics and basically had students developing subsystems. And we've continued that method over the years since then. Every year we have students just trying out different things. We've recently, in the last batch of graduates, we had a student develop a payload that would fit in the same space as the bus that can detect methane to the same level as the Curiosity rover using I can't even TRLS. It's some sort of laser spectroscopy, way above my head, and I'm the project manager. But sort of this is the sort of passion and enthusiasm that you get from students working on space projects. Is they see space and they see the challenge of space and they want to sink their teeth into it. It's interesting and exciting, and there's no real boundaries. That you can't say, oh, don't work that hard. You can't achieve that. If they're given the freedom to explore, they'll come up with amazing things. And I think each generation that comes through our group, we have more expertise in our staff members that we can support them with, but also in our general community as we sort of grow a community through AROSE and through some of our other industry partners. And so it's a really exciting time for us at Curtin. We're 62 days from launch. So in 62 days, our satellite, which you see on the right here, it's just a tiny little box, will be in space. And that's a really massive milestone for us. It's also a massive milestone for Western Australia, because this will be the first time Western Australia has put something into space. And so it's a really exciting thing. Maybe not something in space, a spacecraft in space. I think I heard a protest. We have had experiments fly to space from WA before, but the first time that we put our own spacecraft into space. And for us, it's just the beginning. So we've already got 6 more booked, 6 more spacecraft booked to launch. So it's the first step in an iterative process rather than one-off mission. So we've got a long-term vision that takes us from LowEarth Orbit to the moon. That's a great conversation for another time, or for over drinks after this. But essentially, we haven't set out to do one mission. We've set out to build a program, and having industry partners instrumental to that, and having the support of our broader communities is really instrumental to that. So I've sort of cut across a bit of this, but our approach is looking at how we can bring that capability in at a lower price point, and part of that is by skipping the overhead. So a lot of the time you're paying for space heritage, and often the heritage that you're paying for, because of its very nature of having heritage, means it's old tech. And so people aren't trying out the latest technologies in their spacecraft because it's a risk. As a university, we can take that risk. We can push the limits. We've got a facility, so you can see on the right there, it's hard to tell what it is, but that's actually the CubeSat sitting in a thermal vacuum chamber with a shroud around the outside, which we can tip liquid nitrogen into, get a cryo vacuum environment, and then run heaters to simulate the thermal cycle of LowEarth Orbit. we can spend time in the lab and just destroy things because we're making them ourselves. We don't have to give a bar. There you go, there's a good bar there. 2.5 million is sort of a typical spend on a CubeSat. We don't spend that kind of money. A lot of that is paying for the bus heritage, and so if you would like to purchase a bus from a CubeSat company, you're looking at about $1 million spend all up. Whereas we've generated all the IP ourselves, so that's something that we hold, and that gives us the opportunity to do these things over and over again. We've built 15 of them in the lab and tested them and destroyed them and broken them in many creative ways, and I think that's kind of the approach that we're taking. We're taking this idea of fast fail development and testing to destruction, and really trying to understand the risks in the environment. We've got upcoming partnerships to start working on radiation hardening in the university, and also just the idea of taking that flip from 75% bus to 25% payload the other way around. And of course, as you get bigger, this concept extends. You don't need that many more additional systems as you grow larger. The computer stays the same size. So actually, as you go larger and larger, so what people do is they go from 1U, and then they stack 3 of those together, and they call that 3U. Very creative. 2 of those together, they call that 6U. 2 of those together, they call that 12U, and so on and so forth. And eventually what happens is you get too big, you stop counting in U's and just start talking about kilograms. So 1U is 1.33 kilograms, and so that sort of stacks up as you go. But by condensing the bus, actually, as you go up to 3U, your bus size becomes just a fraction of that. It's 1/6 of the spacecraft is now bus. You go up to a 6U, 1/12. So it's that idea for us of developing a really powerful system in a very small package, and it shouldn't seem outlandish because you're all carrying a phone in your pocket, I imagine, and that's an incredibly powerful machine compared to a lot of the things that fly in space. And that's a tiny, tiny condensed package. And that's basically the model we're looking at, is the consumer manufacturing of cell phones and leveraging those supply chains and techniques rather than bespoke manufacturing of each bit. So when we order bulk PCBs for testing rather than building one ourselves and going through the process. So it's very sort of against the typical curve. We've taken on a lot more risk, so that we expect to see failures during our series of missions. That's an accepted part of the process. And so those satellites are going to be tested in low Earth orbit. So they've got a really limited orbital lifetime of 18 months to 2 years. So that's actually not a massive risk in terms of creating debris or anything like that. So it's a great opportunity to test stuff without risking anyone else's spacecraft or putting large mega constellations in front of astronomy telescopes. So this is a bit of a if it starts. Yeah. So it's sort of just a bit of an idea of complexity in a small package rather than having wires spread out, having those massive number of stacks. They're just subsystems all crammed into that PCB network. And the majority of the systems are wiring. Like the boards you see for different systems carry very few chips, and it's mostly just simplified wiring. And you have to deal with issues like thermal and noise issues, but those are all things that modern manufacturing, modern design techniques take care of really well. And I guess so. The copper color you can see is actually magnetorquers, which is another interesting element of working in low Earth orbit. You can use electromagnets to leverage the Earth's magnetic field to control your pointing direction. So there's a lot of really fun things to try out in low Earth orbit that we haven't explored entirely yet. So yeah, as I said, launching in 62 days, and we'll have our 1U. We have a command station, ground station at Curtin University, and also we're working with our partner Fugro to use Spark, which is the Australian Space Agency funded robotics communications centre in Perth, which is being developed, I believe, mainly in Noongar, but also in Wellington Street, and they're also an AROSE member. Basically looking at building methods of practice sort of methods of practice or principles of practice of how to operate satellites from Perth, and also how to hand over from ground station to ground station to build in redundancy. And a lot of these things are sort of familiar for remote operations in mining. It's one of the great things about being in Perth is there's a really rich body of expertise who understand the difficulty of operating things from a large distance. And that's really a big part of why AROSE and Fugro's Spark Centre have arisen here in Perth. I guess the other interesting element, which is probably a little bit to the side of this talk, is that we have an opportunity coming for high schools also to build payloads as part of our space program. So we've got a really big focus on STEM outreach and engaging kids in building stuff in space. In America, as a child, you can think to yourself, I want to be a NASA engineer, I want to be an astronaut, I want to do stuff in space. And it's very simple. The people come around to your school, they say, hey, do you want to build a CubeSat? And you get to walk along in a CubeSat project with NASA engineers. In Australia, you go, I want to be an engineer, I want to work in space, I'll probably move to America. And we don't want that to be the case anymore. We want Western Australians to feel proud and confident that they can be part of the space industry here in Western Australia, not give up this beautiful place that we live in to be a spacecraft engineer. So I guess the last point to make is just about why is this useful, and why is a little 1U CubeSat going to be useful for looking into Earth applications. And right up front, there's sort of two main areas that I would sort of consider to be the commercial or industry applications of spacecraft, and that's in data collection and in communications. You get the Earth imaging, the thermal imaging, visual field imaging, hyperspectral imaging. That's all really data collection, and it's looking at Earth. Looking at the Earth, collecting data on your sites, your mine sites, potentially, looking at bushfires. CSIRO have a great project currently looking at bushfires, and that's something that we discuss with them regularly. And then also we use GPS, so we use location services. So I guess that makes 3 categories. And so really, with a really small CubeSat, you can already start to look at really broad field imaging, but it doesn't take a lot to get from a 1U to a 3U, and a 3U is actually one of the primary systems doing Google imaging for Google Maps at the moment through a company called Planet Labs. Strongly recommend looking at their stuff. It's incredible. They use 3U, I think it's 4 kilograms satellites. Basically, it's a telescope with a satellite built around it. And that gets so many passes compared to any of the larger satellites. Because they're in LowEarth Orbit, they're expendable. They put them up 100 at a time and they replace them as they burn into the atmosphere. It means the technology develops really quickly. You see iterations of technology, more powerful sensors, better optics coming on board. Instead of these ones that you spend $1 billion on, you put it up there and it will be up there for the next 20 years and the data doesn't get any better. So we've got things like that happening in the space industry, and it's one of the things we're really interested in Earth observations. And I mean, there's a good list here, but I think you're all familiar with the sorts of things that Earth imaging data can give you. But I think the thing to consider is that as we look at smaller spacecraft, we get that rapid coverage. So instead of seeing like a change over a month, you get like we got a pass every day of the same site, and you start to see like being able to compare that real-time change, maybe of a stockpile as it grows, vegetation changes around the mine site, things like that might be really interesting. But yeah, I think I'm running out of time, so I probably should start wrapping up. I guess if I left a thought with you after this talk, it would be that a lot of people think small is going to be really limited, and we used to look at Get Smart and his phone in his shoe. That's stupid. That could never happen. And then I see my boss on his phone, on his watch. This is what's happening here today. The idea of video conferencing was once laughter, and now it's absolutely mandatory. We can't survive this pandemic without it. So I think it's important to consider not why small is different from big, but all of the things that we can achieve with a lot less money, so that means a lot less risk, financial risk, and we can take on more technological risk because we've reduced that financial risk, and that means we can push quickly for technology development, and that means we don't even know yet what's this going to cause for us. We just can keep the pace going and we can find out as we go. It's those unknown discoveries, I think, that will be the most valuable for us all. Thank you.